start? Okay. So good morning, everyone. My name is Shai. I work with IBM Research. And today I'm going to talk about what it's like building and then running a Solr-as-a-Service on the cloud. So first, a bit about myself. I work with IBM in the social analytics team, and I'm a committer and also PMC member of this community for 7 or 8 years. I blog, not as much as I should probably, and if you want to reach me out, feel free to send me an email. So a bit of background. So there are many teams in IBM who adopt Solr and build solutions on top of it. And you've heard in the keynote yesterday of IBM Watson, and there are many other teams. So IBM is a very big company, and many teams need search. They have different use cases. Some of them want to use Solr for just search, even though we are hearing that there isn't any more of just search. Some of them use Solr for analytics. Others use it for key value stores. What makes all of these teams common in that they want to build their solutions on the cloud, specifically on the IBM cloud. And when we started to analyze what it takes to build to put Solr in the cloud, then we realized that there are many challenges of putting Solr in the cloud, and basically many challenges of building cloud-based software in general. So all of them have similar challenges like security, which cloud infrastructure to choose, how to handle Solr upgrades, whether you should build your solution as multi-data center aware or in a single data center. We know that it's not an easy task, and Solr only has these supports in Solr 6. So we know that if you want to have a multi-data center aware solution, you have to really architect it that way. And instead of having all of them solve the same challenges, then we've decided to build a service in IBM that is cloud-based and offers hosted Solr instances so that our engineers who are maybe IR experts at some point, but other times they are not. They don't need to focus about how they should deploy Solr. There is a common question, on the mailing list. What should be the size of my Solr cluster? How many resources to allocate? We want to take them away, take that away from the user. So they, instead of worrying about RAM, CPU, and storage, they can just tell us, I want to index 1 billion documents, and I want to have or to support 100 queries per second. Then we will do the math and figure out what type of Solr cluster do they need, how many nodes, how much RAM and CPU each one gets. And leave our engineers with worrying about indexing and search only. And as I said, not worry about high availability and everything. We have no intentions to re-implement the Solr APIs. We don't have the manpower to do that, and the community is doing a great job at it already. So our intention was to support the full Solr APIs, which turned out to be a bit problematic, as I'll go into details later. And Solr, as well, all of you probably use Solr Cloud, but Solr Cloud isn't really cloud ready. There are many challenges of putting Solr in the cloud, and we had to adapt it to actually do that. Now, we heard in the opening session on Thursday that the direction of the community is to make it more auto fault tolerance and all of that. So I wish that was done earlier, but it wasn't. So I'm going to talk about all the challenges that we needed to face. Okay, now, anyone here developed a cloud software, like deployed the software on the cloud? Good. Well, I think it's fun, but I also think it's frustrating. So you have to make many decisions. So first of all, when you develop cloud-based software, you don't really develop the full stack of the software. So if you have a good cloud, then you want to rely on other services. And therefore, you are not going to focus on developing everything, rather your own microservice, and integrate with many others. So in our infrastructure, we have an authorization microservice. So we don't need to really actually implement it, only integrate with it. Logging, we use the ELK stack, but we don't expect anyone to re-implement that. Service discovery, uptime, what do you do with pages? So when you work in the cloud, if it's a good cloud, then you want to focus on only what you need. What type of infrastructure are you going to use? Are you going to use virtual machines or lightweight containers? Virtual machines have more power, but are more expensive. They take more time to provision versus containers who are lighter. Are you going to use local or remote storage? Especially for search, we know the trade-offs. Software development has its own challenges. First and foremost, how do you test the code? So you can write unit tests for your own code, but since you integrate with many, many services, how do you test that integration? You cannot run all the services in your local Jenkins server. So we had to work around that, and we built different layers of testing. Most of our testing are done on Jenkins, but some of our testing are done on the actual cloud, verifying that we integrate with all the other services properly. How do you perform software upgrades? That was one of the more challenging points, and I'll talk in length about that. How do you migrate infrastructure from one data center to another, or what happens if the infrastructure itself needs to change? Stability and recovery. The one rule that I've learned during this project is that edge cases are not so rare. So think about one Solr cluster with a few nodes, and ask the question, what is the chance of a leader dying during replication? Well, very, very low. When you have thousands of Solr clusters, and you ask the same question again, then for one of them, it's very, very low. But throughout all of them, you're going to have one instance of that happening. So basically, if I could give you only one advice for working in the cloud, is that always assume that if anything can go wrong, it will. And you'll need to code for it so that your software doesn't break in case of these issues. Now, before I get into the architecture and all of that, we had the first question that we asked ourselves is, how are we going to handle multi-tenancy? Now, if you attended the keynote speak today, you've heard that Salesforce chose to handle it by having, I don't know, maybe one Solr cluster and different shards for tenants. And we've considered, either one Solr cluster for all tenants, or one Solr cluster for a group of tenants, or one Solr cluster per tenant. And we've chosen to go on the cluster per tenant architecture, and for many reasons. So there are, of course, security reasons. You don't want to risk that one cluster or one user will accidentally or not accidentally access the data of another user. And if they are put in the same Solr cluster, and Solr itself is not built for multi-tenancy, so it doesn't have means inside that protect the one user from another. So that's of course the trivial one. What happens if one user uploads a Solr config and configures his caches to hold 100 million entries? Then that user will probably run out of memory, but it affects the other users that are running in the same JVM. So we chose to have one Solr cluster per tenant, and in that, all clusters are completely isolated from another. That gives us very flexible ways to control resources. So not all clusters need to have the same, need to be of the same size. Each cluster has full access to the API, so you can create as many collections as they want, have their own configurations. We protect them by having different zookeeper CH roots, so they cannot really access one another. And it also allows us to have one user running on Solr 5 and one user running on Solr 6, if you want to. Now, we've also decided that each tenant can create multiple clusters because there are many use cases for that. So the typical use case is I want in my organization to have different clusters for HR and finance. So that's very easy to set up, but you're still one tenant. Or you just want to have your dev, staging, and production solution built in the cloud. So we don't limit our tenants. So a tenant is a user account, but he can create as many clusters as he wants. OK. So how did we architect that service? I'll talk about 3 layers. One is, let's call it the search service layer, for lack of a better word, which is comprised of many microservices. So we have a microservice that does software upgrades. We have a microservice that handles the life cycles of the clusters. We have a router. We have a Solr monitor, which does a lot of work to make sure that Solr works in this chaotic cloud environment. Now, our bare metal servers, they run as a Mesos cluster, and we use Marathon to manage the containers. And we've decided to run Solr as inside Docker containers. I know there is a talk later today about running Solr in Docker. So yeah, we didn't really face many issues with running Solr in Docker, but Docker is just very lightweight and fast. So compared to a virtual machine, which may take several minutes to provision, Docker containers take maybe seconds. So Marathon, Mesos, and Docker run the entire infrastructure, and each of our bare metal servers has a local storage attached to them, because we know that, especially when you're doing search, local storage is much preferred than remote storage for indexing and search performance. Now, this gives us other challenges, but we wanted to ensure that the users don't suffer performance because it was more complicated for us to implement. Now, I said that each tenant creates different clusters. So one tenant may create a Solr cluster that is very small. We always have high availability factor of 2, or at least now. And then Marathon finds some place in the cluster to put those containers on. Now, another user might come in and create a smaller cluster in terms of number of resources, but another one might come in and wants to create a bigger cluster overall, so he will get 4 instances. And as I said, when you work in the cloud, you don't work alone. There are many, many microservices that you integrate with. Eureka is responsible for service discovery. And Zookeeper is probably the only microservice that I cannot say it's just a microservice, because Solr really relies on it. So we have a Zookeeper service that is first used by Solr, but also by our service to coordinate the distributed operations that we're doing. OK, now, when you come to create a cluster, you need to decide on the size of the cluster. The size of the cluster is measured in units. And we basically, as I said, we wanted the decision to be as simple as possible, not because our users are dumb, but just because the decision has to be something that you can translate very easily. So we've decided to measure the cluster number of units, and each number of units correspond to the actual memory that you receive, the storage, and CPU resources. What I can say is that a size 7 is just 7x bigger than a size 1 in terms of number of resources. That's the math that you should do. At some point, the clusters are going to grow very large, and at this point, we stop vertically scaling the cluster, and we start horizontally scaling it. So you'll start with two containers, and we'll grow the resources of those containers. At some point, we start sharding your data so that you get more nodes, and your data is sharded, and you overall get more resources, but not necessarily vertically. And that allows us to divide the clusters into conceptual tiers, so that when you create a cluster, we we do a very simple math and decide that this cluster belongs in tier X, and that means it's going to get that number of nodes, and every collection that will be created on the cluster will have that number of shards. So just for example, a size 16 cluster, it's not very big. We'll have 8 nodes in total, 4 shards for each collection, and 2 replicas. We want each replica or each core to exist on its own node. And you get 32 cores in total, 64 gigs of effective memory, effective because I don't count the replica in that case. And likewise for storage. Okay, now as I said, software upgrades were a major piece that we needed to solve. And I don't know how you experience upgrading the version of Solr or your own code, but when it comes to the cloud, or to our service at least, it's a very difficult problem. We do not control the data. We build the service, but then users create clusters and deploy their own data. They don't know that we are actually upgrading the software now. So it's very important to us to keep that way. So if you're our user and I upgrade your cluster, you shouldn't be aware of it, you shouldn't be affected of it by it. And this creates some issues. So first of all, in Docker, or for security reasons, I would say we are not allowed to SSH into any of the containers. There is actual user data there or customer data that is not ours. And so we cannot just SSH into the machine, replace a jar, restart Solr, or restart our, I don't know, Tomcat or whatever process, and just be done with it. Also, we have thousands of containers, so this method is not very scalable. A software upgrade means, in our case, a full Docker image replacement. That might sound a lot, but as I said, Dockers are really fast to deploy, and the whole process for one cluster may take very few minutes to complete. And as I said, it's very important that we have no downtime during this process, and the user should continue creating collections, indexing, search, as if nothing really happens to his cluster. There are 2 upgrade methods that we've implemented. Both of them have different characteristics. One of them is the data replication upgrade, where we just replicate the data to the new nodes. It's very expensive because you need to copy a lot of data now across the wire. And, but it's useful for different reasons, which I'll go into later. There is also an Inplace upgrade where we rely on Marathon's ability to pin a container or an application to a host. So the data, the Solr data is there. We just ask Marathon to redeploy the container with a different image. When Solr comes up, it detects the data, and therefore, that's why we call it in-place upgrade. No data replication is happening. This is the default upgrade mechanism that we usually do, unless needed otherwise. So let's just do a visualization of it. The data replication. We want to upgrade from version X to version Y. So we start with 2 containers on version X. Then we create 2 additional containers on version Y. Now those Solr nodes that come up, they are empty. They have no replicas, no data in them yet. Because Solr does not try to do anything in that case. And then we manually add replicas to all shards on the new nodes. And once the process is done, then all of the collections and all the shards have 4 replicas. 2 of them we know that we are about to delete. Now Solr has, for each replica or for each shard, you have a leader. And if the leader dies, then leader re-election happens. Now you could imagine or picture there is a leaders queue. And we first have the current leader in the Zookeeper queue. And then there is a second leader, the second node standing up in line. And only after we create the 2 additional containers, then there are 2 additional nodes now in the queue. Now, if we kill the leader, the current leader, then Solr goes into re-electing a new leader, which will be the second in line. And then that leader will put the other replicas into recovering so that it is sure that they are all in sync. Why is that a problem? If you delete one container, you delete one container, a leader is re-elected, and then you delete the second container while the other replicas are recovering. They don't do any recovering action. They are just marked as recovering in Zookeeper. And the replica is dead, then the two replicas will never be active. No searches will be sent to them, no indexing will be sent to them. Basically, you have a dead Solr, and you have to manually intervene and fix it. So for this to not happen, we use the rebalance leaders and set prefer leader property so that we reassign the leaders to the new containers. And after that's done, and we have leaders on the new containers, it's very easy to delete the old containers because no leader reassignment will happen, and no replica will be left in an unusable state. Before we actually delete all containers, we start routing all traffic to the new nodes so that even if you create a collection or index, then we are guaranteed that it's going to be left or hit the new nodes only so that we don't accidentally delete data that hasn't been replicated yet. And then we delete the containers. It's a very subtle algorithm. It took us a lot of time and failures to get to it. Because as I said at the beginning, when you upgrade thousands of clusters, few of them will hit those edge cases, but you cannot really afford to have any data loss or downtime for any customer. The Inplace upgrade is simpler in concept. So again, you want to upgrade from version X to version Y. You start with 2 containers on version X, but you're not going to replicate any data. So as I said, you just rely on Marathon's ability to pin an application to a host. So you tell Marathon, update the configuration of that container to version Y. Marathon redeploys the container, which means a new Solr instance will be deployed. It will get a different port, but same IP. When it comes up, it detects on the file system there is a replica. So it registers the replica in Zookeeper, syncs up with the leader, and that's it. When Solr is up and report healthy, meaning all replicas are active, all shards have a leader, we repeat the process with the same container. And I don't know if you have a feeling of how fast it is, but it's much, much faster than replicating data and trying for nodes to die and reassigning leaders. So that's the default upgrade mechanism that we use, unless we need the replication one. Okay. So you start with a cluster, let's say it's size 1, because you wanted to either explore the service, or you want to learn Solr, or you don't have much data yet. And after some time, you get more data, you get more traffic, and you decide to resize the cluster. So we allow our users to resize the cluster without re-indexing all of their data. Resizing means allocating usually bigger containers, but overall more RAM, CPU, and storage. So you're guaranteed that you will get total more RAM and CPU, but since we might go across tiers, then some of the containers might be smaller than the previous ones just because you move for a 7 CPU container to a total of 16, but 4 containers share those 16. So each of them is smaller, but overall you have more power. So when you resize the data, or when you resize the cluster, you cannot do an in-place upgrade. You have to do the replication upgrade. So that's one instance when the replication upgrade is useful. Because a size 1 cluster fits on one host, but if you want to grow it to a size 7, there may not be enough room on that host to accommodate it. So we cannot rely on Solr to come up and just magically finding the data. I mentioned tiers at the beginning. So if you resize across tiers, let's say you want to grow your cluster from size 5 to a size 9, then you go from tier 1 to tier 2. And in this case, you're going to get more nodes. So you start with 2 nodes, but now your cluster will have 4 nodes. If we don't do anything about sharding, then you will have 2 nodes serving requests and 2 other nodes empty, which isn't the intention. At least that wasn't the intention when you decided to resize the cluster. So what happens is that just before we start replicating the data, we use the split shard API to split all of the shards. The shards are split on the smaller containers, which we know we have room on them. And then we create the bigger containers, and the data is replicated over, and you move from a one-sharded cluster to a two-sharded cluster. And usually for our users, but I assume many other people, they don't really care how many shards they have, as long as search behaves properly and performs. And okay, now Solr has many collection configuration options. I can tell you that. It's very good for you if you run your own Solr, but if you run a service like we run, it can be destructive. Again, I want to repeat, this isn't our data. So if you upload a config XML which sets the number of documents to cache to 1 billion, and your instance will repeatedly hit out of memory, I cannot really go and change the config XML. I'm not allowed to, and also you can also upload another one instead. And we ran into fun cases of users trying to play with config. So one user, and even though I know it, I didn't think people will do it. One user decided to configure the lock factory to be simple instead of native. I don't know how many people in the room know what the lock factory is, but when Solr comes up, then it tries to lock the index for writes by other processes. A simple lock factory means that if the lock file is present on the file system, Solr refuses or fails immediately to obtain the lock. A native lock factory means that the file can be present on the file system, but it uses native I/O and native file locking. So if the JVM dies and Solr is restarted, then there is no native lock on that file, and Solr can reacquire it. So when users do that, and the container suffers a restart or any issue, then Solr comes up, but cannot even lock the index, cannot use it. People, for some reason, decided to cancel the update log, which sort of beats the purposes of having high availability in our case. So we had to block that. Even though we don't give users permission to write outside the Solr home directory, users try to override the data directory. XSLT is prevented for security reasons. Now, you're not allowed to upload custom code into your cluster yet, at least. So there was no point of letting you configure your schema, the schema factory, update listeners, or really anything, because you're not allowed to put your own jars. And since you don't really have access to the cluster, there's no point of having JMX. So there are many configuration options, and I'm almost sure that there are still some out there that are lurking to bite us. And when it will happen, we'll probably block them too. So I mentioned the Solr monitor microservice, and this is where adapting Solr to the cloud environment had the most issues. So in our case, containers, I mean, this is what happens in the cloud. You're guaranteed to have servers failing, but you want to rely on the cloud infrastructure to just reprovision your data or your application elsewhere. That's the benefits of working in the cloud. And so this is bound to happen. Solr assumes that if there is a replica in the cluster status, and the replica or the node that the replica sits on is not currently in the live node, then it is optimistic in assuming that the node will eventually come up and rejoin the cluster. Therefore, if you have a replication factor set to 2, and one node is down, and even if you have 3 nodes in your live nodes, Solr will not go and add the missing replicas. It will not try to re-achieve the high availability, because if that other node does come up, then you suddenly have more replicas than you wanted. But in the cloud, this is just normal behavior for having containers dying and spawned elsewhere. I mean, this is just what happens when you manage many servers. And so we call it the missing replicas case. When we detect that there's only one live node and one shard has only one replica, then we add the missing replicas on other servers, if there are any. Dead replica, so this is just cleanup. That replica that was on a dead node, it will never be removed from cluster status. That is an issue because Solr manages the cluster status in Zookeeper, and eventually, thinking about a cluster that is active for a year, you might accumulate too many dead replicas in Zookeeper, and we don't want that, so it's just cleanup. There's no actual node to talk to delete the data. The node is already dead. Extra replicas is a case where it happens when we rebalance the cluster. So if replicas on two nodes, but you can move some of them to other nodes, so that results temporarily in having more replicas than intended. But also when you, so we call it the stack overseer for many versions of Solr. The overseer was stuck in that we submitted add replica calls, it timed out, and our monitor didn't know it timed out, so it resubmitted the call. And then after an hour, for a reason that to this day, we don't know why, the overseer was freed, and we added 200 replicas. So yeah, we detect that and then delete them. Okay, cluster balancing. So when we resize the cluster, we split the shards. And what happened when you invoke the shard split command? The shard is split, and two replicas are put on the same node. And then two additional replicas are added on other nodes. Now, those two replicas, Solr does not later tries to move them elsewhere. So we have a node with two replicas, another node with one replica, another one with another replica, and then a free node where we know we can fit a replica on it. So that's when we do some cluster balancing. When we fill missing replicas, our goal is to always achieve high availability. So if you have a four nodes cluster, and you have two shards and two replicas for each, and one node is down, then we always add the missing replica to another node because high availability is more important. When the fourth node comes up, then we'll move the replica to that node. Okay, so in the interest of finishing on time, I want to move on. There are many other fun challenges that we've hit. So close wait, I don't know if you follow the mailing list. Between Solr 5.01 and 5.5, if I remember correctly, somebody changed the max update connections and max update connections per host to 100,000. We track the Solr changes, of course, but we can't see all of them, and we missed that. And we started seeing containers that just stopped talking to each other. Down replicas all over the place, Solr is not able to recover, no updates are sent to the replicas. After some time of investigation, we found that each of those nodes has thousands or tens of thousands of connections stuck in a closed wait state. This is a result of having SSL with HTTP client, not closing idle connections. Anyway, it has been fixed in Solr 5.5.3 and onwards. But if you're on a previous version and you want to override it, then you should put those two properties in the Solr XML. The stack overseer, as I said, I don't know why it happened, but over the last 3 releases, the overseer had gone through many changes, bug fixes. Its queue operation was re-implemented or modified, so we no longer see this problem. But our monitor attempts to call the overseer status, and when it doesn't come back, when it times out, then we know the overseer is stuck. And if that happens for a few times, then we alert someone in our SRE team to go and look at that cluster. As I said, since 5.5, I don't believe that we've hit any such incident. Okay, I said at the beginning that we wanted the users to have full access to the Solr API, and I cheated a little bit. Solr has admin APIs, which are completely irrelevant to our users. There is no point for our users to invoke shard splitting or try to mess with the leader role or try to reassign replicas elsewhere, because that's done by us. If they did try to do that, then they could break their cluster. So we block most of the admin APIs. And also when users create collections, we don't really allow them to specify the number of shards, number of replicas, any replica assignment strategy. So they just need to give us a name and a config name. So the configuration API, our users do not have access to Zookeeper directly. They only have access to our REST API. So we built a REST API to manage the configuration in Zookeeper. Okay, where do we stand? So we are running nearly 2 years in production. It is still a very young service in terms of both number of users and the capacities that we are seeing. People in our organization are moving to Solr, so not all of them finished the transition. Anyway, we run currently a cluster of 400 or so bare metal servers, more than 3,000 clusters, 6,000 nodes, Solr nodes. Again, this might sound like a lot, but this isn't one Solr cluster that needs to handle all of that. So there's a lot of work that we do, but each Solr is quite tiny and only needs to care of its own data. Yeah, we get that many APIs called. The challenging is to keep an uptime ratio. So I think we are done with a lot of the infrastructure work. So now we are very or highly available at these numbers. So yeah, I'm done. I'm willing to take questions. I don't know how much time we have. Yeah, we have like 2 minutes. Yeah.
How does your monitoring work? Like, what service do you use and what do you monitor?
Okay, the question was how do we monitor Solr, right? So on each Solr container, Solr is run in its own JVM. We have another process that's running and talks to Solr, to the Solr API. It just pulls down the cluster status and checks what's in there. The cluster status is very solid and stable in that even if both the containers die, Solr keeps the data, the replicas, the information in the cluster status. So we know where they were, I mean, where the data was. Yeah, we have like one leader across the monitors that does this work, but that's how it works. Yeah. Sorry.
I thought you said that you don't give access to Zookeeper to your client. So if a client has Solr-J, if they have a Java app and if they want to talk to Solr,
yeah, they use the HTTP client. So we implemented an extension of the Solr HTTP client that can talk to our service directly. But then we forward all the requests to Solr.
So all the smart features on Solr-J is not directly realized. You have to go through the HTTP code.
Yes, yes. And we also need to ensure that you can actually talk to your cluster. And the Zookeeper, I mean, Zookeeper is also an implementation detail, just like you heard. The intention is to also make Zookeeper an implementation detail of Solr itself. So I don't know how it will play out, but that's currently what we do. Yeah, you want it.
Yeah, when you split the shards, how do you handle search, query, and update index at the same time?
So that's luckily done by Solr. When you invoke the split shard command in Solr, Solr adds 2 new shards to sub-shards, and the main shard, the parent shard, continues to receive all the indexing requests and search requests. Only when the split is done, then the 2 replicas that come up in the sub-shards replicate the missed events from the parent shard. When they are up to date, then the parent shard is put into an inactive state, at which point it will stop receiving indexing requests, and Solr completes or fills up the missing replicas per the replication factor settings of the collection. Yeah. The data replication upgrade, being the slowest of the two, is used when we resize a cluster because we need to allocate more resources, and the containers will probably end up in a different host. Or when we migrate the infrastructure, like we needed to move from one data center to another, we cannot move the machines. So we just allocated new containers and replicated the data over.
So for version upgrades, you still do in-place upgrades?
Yes, for most upgrades that we run, and this isn't just a Solr-specific upgrade. So the container that runs Solr has Solr code in it, but also other code. The monitor code is also running there. So anytime we need to update that code, we do an in-place upgrade, usually.
The second question I had is, using Mesos and Marathon, right? I'm just curious. Do you guys look at Kubernetes, or was that collaborated and
Yeah. So this wasn't my decision in that there is a platform team that looks after or looks at different technologies. Mesos and Marathon is the current choice, but I know they are looking at Kubernetes as well. We might actually move to it at some point. It highly depends on what exactly we get from it. As I said, the Marathon pinning or agent pinning is a very critical feature for us to avoid those expensive replication. And yeah, I can say more about it. Okay, I'm being pinged to stop, so I'll wrap up, and then you can come ask me a question later.